Hey there, Internet. I watched a video today and it made me want to cry. It's not that bad, but I really hope I can help this guy out. His name's Artisan Makes. His videos are production quality value, orders of magnitude better than anything I've ever produced. But this, the thing is getting stalled. It seems like, I don't know, all the footage is sped up, so it's hard to tell what speed he's actually running it. It seems like he's running this thing way too fast. And this idea, I think, is maybe a good idea, but not without a bunch of other stuff to happen first. So what I want to do today is I want to talk about what you might need to do before you go through and try to do something like this. There's some more fundamental and more basic things that can be done. You need to have an indicator. You need to do some measuring, and hopefully you'll be able to avoid that. So, that's not a sound that should come out of your lathe. If your lathe sounds like that, you're probably doing something wrong. You can see how much movement there is. Now, I don't use a carriage lock. I think a lot of people make these because they just have a crappy setup down here with the looseness of these gibs. There's just slop everywhere. So if you want to have any prayer, you have to make a carriage lock. And what that essentially does is it pulls everything down tight against these prismatic ways. And this bottom way gib, I guess it's called, it won't be doing anything at all because all the work is going to be done with this clamp. This is a great example of the issues with with the dovetails. So here's a normal kind of like end on lathe view. We've got the cross slide here, and we've got the ways, kind of this light beige color, and then we've got the work, which is red, and we've got our chuck, which is blue. And if you think about how a mini lathe is set up, when the cutter is rotating that way and there's a tool on the cross slide, it's going to push down on the cross slide, and that downward force is going to kind of like, there's some vector, I don't know exactly what it is, but it's going to push on this prismatic way here. And if there's any give in this setup, some force, net force down here in some situations, but then there's also a possibility that you get a force here, and you may get some, when everything's chattering, you may get kind of forces that go back and forth. The main area where you're getting your registration when you're cutting on the lathe is this rear way and this front prismatic way. And the majority is through this, the way I understand it, is through this rear prismatic way. And other than scraping your cross slide in these surfaces here, there's not a whole lot you can do about whatever you have. Now you can level your lathe, which is essentially, you can kind of adjust somewhat how it sits, and the body, there's a twist actually that you can exert on the body to straighten out the ways somewhat based on how you bolt it to whatever you have set up on. But we're not gonna talk about that exactly right now. That's beyond the scope of what I really want to describe. The main thing is the mini lathe. This piece and this piece down here, these are separate pieces. This area here that I'm shading in, and this area here are separate pieces. And the way that it works is you've got bolts that run through here. It might actually be better to draw it like this. So you've got like two bolts with countersunk heads. And they're gonna push up this way. And then you've got you've got the surfaces that are split by some distance. And then you have grub screws. This is a terrible drawing. But you've got these grub screws, and they're kind of pushing these two pieces apart. So the bolts are pulling them together, and the grub screws are pulling them, keeping them set to a particular distance. And so that all that stuff is in here. What you get is you have a pivot point in the middle of this that is going to create kind of like a rocking moment around the pivot point here. So you have two kind of moment forces where these things can flex, and this is like a big lever acting on your pivot point here. So if that's the center of your pivot point, this point here, which may be in contact with your way, it may not. These are not machined surfaces. So you have a point out here, and it's rotating. So the point that has the most movement is actually this point out at the end here, because it's furthest from the pivot. So you've got this really crappy, this grub screw and bolt arrangement, which doesn't have any rigidity. One of the best things that you can do is use a tapered gib to make this adjustment. You can't have this, there's got to be some space in between these two surfaces, or you're not going to be able to move the cross slide. But a tapered gib will allow you to make a really fine adjustments there, and then have them stay the way that they want. If these grub screws back off because the lathe is chattering, or even if these bolts back off because the lathe is chattering, you're going to get this rocking, pivoting action here and here, and that's going to cause a bunch of problems. So again, if you go back up to where the cutting forces on the lathe are, they're going to be acting on the compound if you have a compound setup. If you have a solid tool post here, you get a much greater transfer down into the actual cross slide, and they're going to go into the ways. But if there's any forces going the other direction, down here, you just have no. There's nothing rigid about this, and so the video that kind of inspired me to talk about this, the way that this was set up was he put his this is probably more steeper, but he put his cutter in a tool post back here, and for some reason he couldn't reverse his lathe because of his motor setup. The spindle's spinning this way, and so that's going to create this momentary force around your pivot, and your pivot's like all the way down here. So that's going to create a force going this way down here, because this is going to want to pick up, and then that's going to want to rotate against this pivot point. So assuming you've got a good connection down here, all that rotational force is going to end up over here with this guy rocking up, and then you've got this pivot point, which, it's going to contact the bottom of the way, which is not machined in any way, and then this will flex back and forth, and then this will oscillate back and forth from the cutter. That's what's going to produce all of the weird chatter that the guy saw in his video. And this grub screw and this this bolt arrangement on the normal mini lathe, assuming that you don't have a really spectacularly finished one, that's going to create the majority of for this setup, that's going to create the majority of, I think, the motion. Because if you look at the points, the distances between these points, the forces, they're going to have the largest impact out here, because this is the furthest thing from all the pivots. For a tapered gib arrangement, so you've got a motion back and forth this way, and then what happens is these two, this surface and this surface, stay parallel, but the distance increases, right? And so if these are machined correctly and then they're set up parallel to this surface, you're going to get a really nice fine adjustment here. The alternative is really, you've got, unfortunately, I'm fighting Microsoft Paint because it hasn't been updated in 35 years, but the colors, I don't even want to talk about it. I hate it. The alternative, if this is a bolt and this is a bolt, is instead of having the grub screws hold these two surfaces away, that you put some shim stock in here. And the shim stock is impossible to draw on this ridiculous, stupid program. There's got to be a better annotation program than this. The shim stock lays in there. There's got to still be a small gap, but the shim stock is the thing that is going to allow you to keep these two surfaces evenly spaced. And unfortunately, it's kind of a pain in the ass, but you shouldn't have to do it very often. The surfaces will wear somewhat, but not that much. They're really, really big surfaces. So, this is quite a lot of work to put a tapered gib arrangement in there. It's much easier just to get some precision shim stock and get the shim surface. Now, you still have a decent amount of leverage because, you've got this whole distance between, or you have this very small contact surface, and then it's acting like a big lever. But the shim stock gives quite a bit more surface area to make this solid than the grub screw and bolt arrangement. So I think that's the easiest fix to make this solid. Now what you should do is you got to measure this to see how bad it is. So let's go out to the actual lathe and we'll actually measure it in a couple different setups. And I've already done some tuning on mine, but you should measure yours and figure out if it's a problem or not. Here I am out at the lathe, and originally this video was just going to be to address parting, but then I decided, I might as well just show you all of the places that you need to think about when you're tuning one of these lathes. And the idea here is really baseline your lathe, measure it, and once you have the measurements, then you're going to have to make some decisions about where do you want to invest your time. All of the mods available take pretty decent amounts of time. So there's some simple things you can do, like adding a thrust bearing here where the cross slide lead screw interfaces with the housing. There's some really time intensive things that you can do, like scraping the interface between these prismatic ways and the bottom of the cross slide. There's a whole bunch of different things that you can do. Before you do any of those things, you got to do a baseline and then use the adjustments that you have on the lathe and compare it with the baseline. So measure it, make the adjustments, get it as good as you can get it, and then compare it to your baseline and figure out how much you've actually improved things. That'll help inform you as to what kind of mods you might want to do above and beyond just going through the normal adjustment process. I think some people jump into the mods without actually doing the really basic adjustment stuff. And if you don't understand that, it's a pretty easy mistake to make. So this is not only going to help you with your parting and help you understand how your lathe is reacting to your cutting forces, but it's also going to give you that baseline measurement so that as you make improvements, you're going to know how much of an improvement that you've made. It's really hard just to look at these things and understand quantitatively, did you have any kind of a good impact, and are you in the spot that you really want to be? So I'm going to walk through the whole lathe. We're going to talk about the adjustments that I've made and what I would consider is two decently tuned lathes and where their tolerances are and how much slop there are in all the different interfaces. There's a whole bunch that we're going to walk through. So what I've got here is just a magnet and a parallel. What that will allow me to do is I can put the indicator out here, and this is going to magnify how much movement we have here. So we just want to see about roughly. I've got it set up on 0, and so what I'll do is I'll lock in. So you can see right away when I lock in the split nuts, I've got 7 or 8 hundredths of a millimeter of play out there. And if I if I move it back and if I just do some wiggling, you know, I have about 5 or 6 hundredths of a millimeter, maybe like 2 thou of an inch all the way out here. Now, we'll move it in closer. And obviously that won't be as dramatic. At this point, it's still about 1/2 thousandth. So now I've moved it closer where the ways are actually fatter. Again, this bottom surface has not been machined. You'll see I have about, you know, about 1/100th of a millimeter, which is real tight, especially across this surface, which from the front to the back here is about 120 millimeters. That's about 100 millimeters. This setup works pretty well, but I think when I got the lathe, I'm sure that these were not even adjusted. They were set up the way they were from the factory, and there was a lot more play in there. So what you should do is you should check this, and the easiest way to check the back one is just you can put it on the surface here. You can do it like I did, and push it out and kind of magnify the effect a little bit. If we want to look at how much slop we have on this front one, we're going to have to move the indicator a little bit. So let's just take a look and see how much slop I have where these two surfaces are mating. So now I've got the indicator set up on this point, and we'll just we'll engage the half nuts, see what that does. So that's about 4/100ths of a millimeter, just engaging the half nuts. And if I push it around, it's about 4/100ths of a millimeter. And I think that's probably about as good as I can do. Again, this surface isn't at all machined. It's this is better than my other lathe. Actually, it feels much smoother than my other lathe. But I don't think you can really rely on this. And if you need to travel, you need to have some give there. So that's I think one of the things that isn't really explained very well when people are talking about tuning up these lathes on YouTube is the you know, the way the grub screw arrangement works, and how non-rigid it really is. Now, when you're cutting, the lathe is pushing down kind of all through here, and so those forces end up on this prismatic way, and you know, if it's a steady cut, then there shouldn't be any oscillation at this point. But if you're cutting and the cutter's digging in and then letting loose, that pressure is going to end up with this kind of bouncing between these two surfaces, and that's going to create chatter in your cut. The next area that on this mini lathe, there's not a whole lot you can do, but the distance between the bearing and wherever your cut is a big lever, right? And so it doesn't matter how much you've done anything as far as modifications, you're always going to have, there's going to be some natural frequency based on how much flexibility there is and the stiffness of kind of all of the pieces that run out to here. So I've got the indicator set up on the end here, and if I press down pretty hard, you can see that there's a couple hundredths of a millimeter of give at this point. Now, if we do the same test back here, again, if you understand how a lever works, you're going to see much less movement. So that's about this, probably even more force than I had before, and you can't really see any movement on the indicator. A little bit there. Yeah, there's actually, weirdly, if I push up, it moves, and if I push down, it moves. And what I'm going to guess is that I probably don't have enough preload, or there's something funny going on with the way my bearings are sitting in the headstock. So there's a small amount of give there, but once I push it down, it doesn't really give. So if you had a smaller chuck that with the same amount of stick out from your chuck, you'd have less movement because the length of the lever is different. When you change the length of the lever, it's kind of like a tuning fork. The natural frequency is going to change. And so a longer lever is going to have a lower frequency. So when you're running the spindle slowly, when you're trying to do a parting cut, you're also going to be lowering that frequency. So I think those lower frequencies turn into the kind of chatter that you see when you're trying to do the parting. And if you shorten this, the frequency will go up, and that means that the tool's going to be digging in. It'll still be moving back and forth, but the amplitudes probably are going to go down, so it's not going to be going back and forth quite as much. And the frequency of those back and forth movements are going to be much higher, to the point where it may produce a surface finish that's acceptable. So there's not a whole lot you can do with this for this particular lathe. I don't think you can get much shorter of a chuck. On my other lathe, I'll show you. Well, let's just go over there. I'll show you my other lathe. Okay, so here's my other lathe. This is a much bigger lathe than the mini lathe, and this is a 4-jaw chuck that I got with the lathe. And if I measure how far we have about 85 millimeters from the spindle boss to the end of the jaws, and I mean that's a pretty big lever. And then there's another, from here to here, you've got something that you cannot change, but it's at least 35 millimeters to the face of the headstock. So that's over 100 millimeters of stick out. And then if you're, let's say you have 20 millimeters more of stick out on your work, and you're trying to part out here, that's 150 millimeters of flex that you're creating, that the bearing has to then try to compensate for. And again, the relationship between the distance from the length of this lever arm and the frequency is the longer that distance is the lower the frequency will be. So I've got this guy here that I machined to fit on the boss of this lathe, and you can see that if I hold this up to where it actually seats, the length of the lever arm that I get is, 55, between 50 and 55 millimeters, and it is completely, parting with this versus parting with this is night and day. I mean, I get no squeaking. I can part quickly in steel, no problems at all with this. It can be a real pain in the ass. There's not much you can do about the length of this lever other than get a different chuck. And with the mini lathe, there's only so much you can do as far as the chuck's concerned. But that is another major thing when you're parting that will influence how well your parting performs. There's a bit of glare. I apologize. Yeah, I went through a bunch of stuff, and I actually started editing the video, and I realized I didn't even talk about the slop in any of the lead screws. But all of these lead screws are going to have slop. That means that on your cross slide, you got a lead screw in here. There's some slop. There's some nuts to adjust it here, but there's also a whole bunch of stuff inside of the thing that holds the handle together that there's issues with. And there's a bunch of different mods that you can do. I made a video on how I actually modified this guy here. You can watch videos on how to adjust these nuts for the actual cross slide nut. But really, you got to make sure that you measure it so you know what you have, right? All you really have to do is just pull and push. Pull and push. It's real straightforward. And here, there's about 8 hundredths of a millimeter of backlash this way. And that backlash, when the tool's cutting and it digs in, and then that material goes away and the tool flexes back up and is clear, there's gonna be some vibration back and forth this way. Again, when you have a solid cut, when you're continually removing a steady amount of material, there's going to be a force down on this prismatic way. There's also going to be a constant force on here. But if you're manually feeding the thing, you're going to have a real hard time doing any kind of constant force cutting, because you just don't have a way to do that. That's actually a really good reason to have an electronic lead screw, because the electronic lead screw kind of monitors the speed of the spindle and then matches that, so you get a constant surface feed rate. But that's a bit outside of the scope of this particular video. So you want to baseline this this adjustment here. I think this is not bad. Anything less than 1/10 of a millimeter is probably not bad. So your main lead screw, the one that does your power feeding, also has potentially slop in it. And there's some adjustments in the gib. There's some mods that you can do. Again, what we're doing here is baselining. But all you do is you lock in your half nuts and move it back and forth. So you can see that here I have about, I don't know, I want to say 3/4 hundredths. That's probably too tight, but there's very little backlash in here. Again, you can kind of overdo some of these things. So if you have the compound on, you also have to check that. So there's 3 screws where you have backlash, and then there's all the other surfaces you have to worry about. So here's my other lathe, just for a point of comparison. And on this lead screw, it's about 2 or 3, very little. It's actually much better than the other one. And I just want to show the, this one, I didn't do the mods that I did on the other lathe. I just put a thrust bearing in there and then dealt with the tightening of this particular bolt. It seems to be producing a pretty good result. So it's literally just a 10 millimeter thrust bearing, maybe 12 millimeter, I don't remember. But it's removed quite a bit of the backlash from the lead screw itself. And so it's going to be a combination of the way that the screw comes through this assembly here, and then the actual nut adjustment, which is the nuts attached to this part of the cross slide. The next thing I want to show is the interaction of the dovetail on the cross slide. So as you can see, I have a solid tool post here. There's going to be the same give that I described before. I have these shimmed as well. The mechanism for this lathe and the mini lathe is exactly the same with respect to the registration against this bottom surface of the way. This is very poorly machined. I tried to lap it in, but it didn't do a whole lot. So if I try to pick up on this, or let's latch in the, you can see how much movement just happened there. I mean, it jumps at least 4 hundredths as I lock in the cross nut, the half nuts. The cross nuts, the half nuts, it's all the same. So there's definitely some give this way, but actually let me lock it in because I'm going to be torquing it this way. There's also some give between this surface right here and the dovetail surface here, which is, is adjusted through these gibs. And so the way that you check that is you grab your tool post and you rock it back and forth this way. Now, some of that movement is going to be maybe some slop in the lead screw, but the majority of it, I think, is the dovetails, and you have to have some slop in here, otherwise you can't move it back and forth. But I think like this setup is pretty good. It's pretty decently tight, but you want to measure it. You want to figure out how much of this kind of movement that you have, and that's going to be really driven. The only way that you can really address that is either through scraping in these surfaces to make a better contact, or just a simple adjustment of those gib screw tighteners. Now, this would be another great opportunity to have a tapered gib, and if you've ever worked with adjusting a tapered gib versus these awful things, you would definitely be preferring the tapered gib. The problem is there's just not a whole lot of material available to make room for the tapered gib. And machining something this thin, this is only 4, maybe 5 millimeters, but it's 150 millimeters long. I mean, it's pretty difficult to machine something like that. So to make this a tapered gib is somewhat of a challenge, and I think that's why most people don't even try, doing that mod. I think if you reworked your cross slide, you wanted to give up a little bit of space as far as the swing of the lathe. Oh man, that was a mouthful. You could make this a little bit bigger, and you can make it a little bit bigger out here. That's going to impact how far your tailstock can move in and out, but the advantage of having a tapered gib here would be pretty big. But again, you have to measure this. Now there's another area of slop that I just want to demonstrate real quick for these dovetails. The next area here is the slop on this axis. And if I've seen a ton of YouTube videos where the guys are cranking in and out the cross slide after they've made an adjustment on the gib, and they're like, oh, it's real smooth and everything. But the thing, you can see it. You can look at the edge over here, and you can see that as they crank it, it's literally wobbling back and forth like a millimeter. So anyway, keep an eye on this dial as I wind it in and out, and you can see that there's you know, I don't know that this is precision machined as far as the relationship to the dovetail, but you can see that we're growing so that this is cocked out this way. Now, I don't know how much of a problem that is. It doesn't seem to be like, you know, over the course of 40 millimeters, it's 1/100th of a millimeter, but just, it's not wobbling a whole lot. And if these gibs are not adjusted where the contact pressure of this is somewhat even across the whole length of the cross slide, what you're going to have is you're going to have this thing, it's going to hit friction, and then it's going to push and wobble and do all these sorts of motions. Now the other thing that you can do to check it is get it to its kind of extreme position. Well, actually, let's wind it all the way out, and then I'll really push on the tool post, and you can see I've got about 5 or 6 hundredths of a millimeter at this point. Now out here it's going to be even worse. So out here it's going to be closer to 10. And one of the reasons for that is that there's from back here to the face here, there's, you know, 50 millimeters where there's the gibs and the dovetails are not having any contact here. And this adjustment and this adjustment are doing literally all of the work to maintain the rigidity of the cross slide. If we go back in, the other place to check this is in the back here. So now I have the indicator set up back here, and it's not doing anything. It's definitely motion in there, but let me lock the... Okay, there we go. That might actually be a give in the lead screw. It's real hard to twist it from back here because I don't have anything to push on. But if I have this plate set up and a bunch of other crap, I don't feel like taking it apart right now. What you want to try to do is shimmy it this way and see what happens. And then the other thing you can do is just crank it in and out and see if it's moving a whole lot. You can see here, there's a little bit of tiny movement, but there's not much. And so if you've got all this slop in here, when you've got all this, your cutter's going to be out here somewhere, and it's pushing and chattering and moving all around, and it's going to create some momentary twisting forces, I'm sure. That means you're going to have some problems with your cutting, particularly if it's interrupted cutting, and you're going to have to make some adjustments to your gib screws. It's something I see on YouTube lathes. You just, if you watch them, and nobody ever seems to measure it. They just they adjust it. It's, oh, that feels good, and then they don't do any measurement to see how much slop they actually have. So you have to have an indicator. You have to baseline your machine to figure out where you're at, and then you got to try to adjust it based on the quality of the machining. Like, there's only so much you can do with respect, unless you want to scrape the surface. So that would be my advice for anybody who's, you know, trying to get better, smoother parting, is to do those two things. Now, if you have a compound, you have a whole nother set of issues. If you have a compound on here, not only do you have this thing that can slop around like this and like this, but now you've multiplied that by all of the slop that you have in this mechanism here. And what I found is, actually, let's take this over to the vise, because I've never been able to adjust this thing so that it doesn't suck. But let's put it in the vise, and we can measure it in the vise. We've got it set up in the vise, and you can see right away as I crank this, look at the thing jumping all over the place. Now I've tried to adjust this. I think I need to scrape it. I think it's just the machining on this is so poorly done. There's not much that I can do, but your first indication is, as I said before, is can you crank it without having this kind of crazy jumping around. The other thing is you can just kind of twist it this way and get an idea of, if your vise isn't moving all over the place, you can get an idea of how much slop that you have. So the other thing I want to point out is, now I don't use this style tool post, but imagine there's a tool in here that's sticking out this far. See, I want you to notice how much longer this is than this, okay? And once you get to a position out here somewhere, number one, now you're introducing this motion here. Let's actually just take a look and see how bad that is. So there's, wait, well, part of that is my vise is this particular vise is absolute garbage. But there's 1/1500ths of a millimeter in there without doing a whole lot. So that means if there's 1/1500ths of a millimeter here, out here it's that much more. Okay, and at your tooltip it's that much more. So you've got this in a dovetail. The slop we have is this motion, and we also have this motion. And once you combine that, your tool is just wandering around in space. So this is the reason that getting the compound out of the equation is huge, because you have one of these joints in the compound that can go this way and go this way, and then you have the other one on the cross slide that does the same thing, and then you have the mechanism that holds everything down to the prismatic ways. And when you multiply all that together, plus you've got your cutter out here, so all those forces have to get down to the cross slide, but you've got a big lever all the way out here that's amplifying everything. That's the reason that, if you can, make a solid tool post and get rid of your cross slide, your compound. I can't get that right. Get rid of your compound, and you're going to just immediately, that one little change is going to eliminate all these areas of inaccuracy that you're going to have in your little lathe. So to quickly summarize, the natural frequency, which is going to be driven by the rigidity of your bearings and the size of your headstock and the materials and their flexibility of the materials, in combination with the distance between where you're cutting and the headstock, there's going to create a natural frequency there. The longer that distance is, the lower the frequency is going to be, and the worse your surface finish is likely to be. If you change the speed of the spindle, this is why sometimes speeding up the spindle will produce a better cut, and sometimes reducing the spindle will produce a better cut, because that's going to impact somewhat which resonant frequency shows up in your cut. Now on a mini lathe, again, there's not much you can do about it, but on a larger lathe, if you can get a chuck that has a smaller distance between here and here, and shorter, stubbier jaws, and a couple other things, you may be able to improve things pretty easily that way. The second thing is the mechanism of the mini lathe to kind of hold everything in place as far as the cross slide is concerned, connecting it to the bottom of the ways, is garbage. And you should either think about creating a tapered gib that's much easier to adjust, or using precision shim stock and getting rid of the grub screws. The shim stock and grub screw method is easier to do, but it is fiddly. You're gonna have to size different shims in there, and then do a bunch of measurement to see if you're where you want to be. And if you have any tight spots like I do, once you get out towards the end, there's not much you can do. On my other lathe, I actually have a tight spot right up towards the headstock, And so if I'm out here somewhere, it's much looser than it is if I'm over here. So there's, other than trying to scrape in the ways, which I don't really necessarily recommend unless you really know what you're doing, you're going to have some slop in there. So you got to measure it, and then you got to move it around, and you got to iterate on it to figure out what the right thing to do is. The next thing is to measure the wobble as you wind in and out your cross slide, to measure your wobble. So that's this motion here. Measure that wobble as you adjust your Gibbs screws, and then measure how much slop you have this way in your dovetails. Then I would say have a solid tool post and try to have it so your cutter is not, the further out your cutter is from your tool post, the more leverage, the more twisting it's going to put on the whole thing. So it's going to take this side of your if your cutting forces are down and out here, it's gonna make everything go like this. So you want to have the cutter as close to over the top of the contact area on the dovetails here as you can. And if you have to use a compound, you're going to have to go through that whole tuning setup in either case. So I would say all of this is important, regardless of whether you're cutting in reverse with the tool behind the work, or if you're cutting in forward mode with the tool in front of the work. If you're trying to flip the cutter upside down and cut from behind, it's going to create a lifting force here, which is going to translate to a lifting force in the front of this, where your prismatic ways are on the bottom of that surface. And again, if you haven't made the adjustment down below, and it can create a frequency, and that can create additional chatter and ruin your ability to get a good surface finish. So hopefully that was helpful. If you have any questions, leave them down below. I probably made some mistakes, so if I've made some mistakes, please help correct those mistakes by leaving a comment, and thanks for watching.